So shown here is what you see is an image of a row of Aurora supercomputers, and there are actually more rows like this behind the system. And if you look at statistics, right? So we have 166 racks for compute. There are other racks for storage and service. And if we just count the number of nodes in the compute rack, right? We have over 10,000 nodes. And in these, each of these nodes has not only one, but two CPUs, 6 GPUs, and a number of memories. There are memory module for HBM on the Sapphire Rapid side, and HBM for PVC, which is a GPU, and there's also DDR on the Sapphire Rapid side. And so you have to pick which type of memory depend on the characteristic of your application. In addition to memory, you have multiple network interfaces, and I'll show later, there are non-uniform accesses to different devices, or the memory or even the network of PVC. So mapping these your application processes to the right CPU and the right GPU and the right NIC is important. So shown here is an exascale is a node. I wish I could let me stand in front of it so you can see. It's small on my screen. So on the right is a diagram of an Aurora node. And on the right, you can see two blue boxes that represent the Sapphire Rapid CPU. And toward the left side, there are 6 boxes fully connected. Those are the GPUs. And then the green boxes on top and bottom are the network interface. And what you see is that there are memory modules in orange next to the blue boxes for Sapphire Rapid. You have DDR on top, and then HBM inside the blue box. And what you see here is that there are memories that are closer to one CPU than the other. And so if you map it to the right memory, then your accesses will be a lot faster and you get higher bandwidth. If you didn't do that, then you might have to communicate over the purple line connecting the blue boxes. And those are the UPI links, and they have very limited bandwidth. It's like sucking water out of a small straw. You won't be able to get a lot of data fast. In addition, you see that the blue boxes connect to each of the blue boxes connect to the 3 GPU on the left, and the other blue box connect to the other 3. So communication from host to device and back would be faster if you go if you map your processes to the right CPU. Let's say for the top 3 GPU, want to map it to the top CPU.
They were having a little trouble on Zoom. See, there we go.
Let's see. Can we? Oh, okay.
I went to presenter mode, so
can I see now? Better this way. So what else? So so ideally you want to when you launch a process and that process offload to a particular GPU, you want to keep it in the same would say domain or the same or the closest right or the tightly connected component close to it. So HPC center like Aurora, for instance, right? They provide default mappings that should work most of the time. And you can start out with the default mapping. But for fine tuning, that's where for debugging, it's good to know where your process maps to. And which particular GPU or even a tile or stack. So for PVC, we have two tiles on a GPU, and you need to know which tile it's mapped to, and which process, which core it runs on the whole side, and then which NIC handle the communication. Typically, now you don't need to worry about the NIC, NPI, or we'll figure out which NIC we use. But for CPU and for GPU mapping, it's good to be explicit so that when they change any default, you're not your application is not impacted. Or when you're debugging, you need to know specifically where something goes wrong. And it's good to know the ID of the core as well as the GPU and the tile. So ideally, you want to map NPI processes to the right socket. Let's say if we look at the diagram, it's a good idea to draw a line across the two blue boxes and the 3 and the 6 PVC in half. The top part in what I label as socket 0 is a separate, think of it as a separate core, separate node, and the bottom is yet another separate node. Although for Aurora it's within the same node, it's good to isolate them so that traffic on the bottom stay at the bottom and traffic on the top stay. And so CPU binding can be achieved several ways. One is to use something like NPI or NPIG. For GPU affinity, we use a mask that can be set. And then for memory, we can either use NPI again. For inputs, there's a -mem-bind list that you can specify the memory to map to, or you can use HumaCTL as a public command line to map to specific memories. So how are these labeled, or what are the ID of the core, the PVC? Right. So if we look at the top portion, right, socket 0 or CPU socket 0, there are 52 cores in that blue box, and the label, the ID of the core on the first CPU socket is go from 0 to 51. And shown in the little text there is how you would select or how you would map processes to a particular set of cores. So let's say you have trail rank, then you have trail field separated by commas. Is a comma? Trail field, one for each process, and then you can give a range of core IDs. So on the first socket would be any ID from 0 to 51. For Aurora, the first core is reserved for OSs, so you don't want to use core ID 0. In fact, now you cannot even run the application on core ID 0. So typically you would pick, we start from 1 all the way to 51. And then on the second socket, I start from 52 to 103. So that is the ID of the core. There's hyperthreading, and hyperthreading start from 104 for the first socket and go and there are 52 hyperthreaded logical core, and then same thing for the second socket. And for PVC, there are two ways to label these GPU. There is a flat mode where, as you see in the text one of the GPU box, you can see that two colors. One is pink, the other one is orange. And that represents different tiles, the two tiles. And in a flat mode, each tile is a separate device. So there are 6 tiles on the top portion, and the ID go from 0 to 5. And the bottom set of tiles go from 6 to 11. So that's how. So if you use flat tile key, then that's how you label them, and then you can set your mask to select one of those tiles. Or if you use traditional hierarchies, it's called composite, where you have a separate ID for the GPU, and then 0 represents the first tile, and 1 represents the second tile. So for the first GPU would be 0, and then dot 0 for the first tile on the GPU 0, and dot 1 for the second tile on GPU 0, and same with 1 and 2. And so that for the GPU. For memory now, we have on the GPU side there's only HBM, but on the CPU there's both HBM and DDR. So DDR has a lot more capacity, lower bandwidth, and HBM has only 64 gigabyte per GPU, per CPU, but it has much higher bandwidth. So for flat quad mode, which is default at Argonne, then the DDR is labeled as 0 and 1, right? So 0 is for the DDR module in socket 0, and 1 is in socket 1. And then HBM is labeled as 2 and 3. So 2 is a HBM module on socket 0, and 3 is on socket 1. So how do we put it together? So let's look at the CPU binding. Because there are 12 tiles, you might typically see 12 ranks, right? 1 rank for each tile. And here, because there are many more cores, there are 52 cores, 51 if you exclude core 0, then you can assign multiple cores to 1 rank. And that particular rank may have multiple open empty threads, so it might use more core than it might use all the available cores. So let's say I only want to assign 2 core for each rank. Then you can see the cbind list there. So for the first rank, that's 1 to 2. And the first second rank is core 9 to 10. Third rank is 17 to 18. I label them in blue because those are the ID for the first socket, and the 53 and beyond are the ID for the second socket. So these 12 rank 6 run on the first socket and 6 on the second socket. Or you can choose to give more cores to each rank. So for something like QMC it actually uses 8 threads per rank. And so at one open thread per core, and therefore it needs 8 core for each rank. For ResNet 50, I found that if I give it more core than necessary, then the thread or the process migrates from core to core, and you might see low performance. And for 24 rank, you can take the 8 core per rank and then sort of chop up the range in half, and now you have 24 fields for 1 for each rank. And you can see that with 96 rank, that 96 field, in this case, Lamb and Hack both use 96 rank per node, and they have OpenMP thread running. So they want to run 1 thread on the first hyperthreading, and a second thread on the second logic core, which is also have a thread context. And how do you map to a specific GPU. Typically, we use something like shown here on the left is the code for the wrapper script. And the wrapper script, all it does is it calculates specific ID for the tile. So for flat, then you have fill tiles. But for this one is using the hierarchical where they have to determine the core ID, the GPU ID as well as tile ID. And it uses a local rank ID for it. So you run fill ranks in a node, then the ID goes, the local rank ID goes from 0 to 11. You use that value to calculate the ID, and then that is used to set the ZFTD mask, and that will place the offloading kernel for a particular rank into a specific GPU ID, GPU type. The other thing that it does, the wrapper scripter is mapped to specific memory module, and if you choose if you use one DDR, right, then it will the rank that run on the first socket will get the memory ID 0. But if you want HBM, there will be 2 for the first socket. And if the process is land on the second socket, then the memory ID will be 3. And so I've set the NUMA to use NUMA CTL. It said my preferred memory is let's say a 2, which is HBM on socket 0. And then the $$ is the rest of the argument passed to it. So on the right, how you would use it. Right? So you set the CPU ID, you call it MPEG using the CPU ID list. And then you invoke the wrapper script, and then the application binary as well as parameter are passed after the wrapper script. And the wrapper script will grab the stuff after it, right, and then execute that with NUMA CTL. And so when you long this script, right, it will land the process will land on the CPU ID list that you specify, and the ZFT mask is set how which PVC tile a rank offload to, and then which memory on the host it uses.
So if you're running this through a scheduling system, does this vary from node to node, or you would just use the same?
You use the same. It's all the nodes are pretty much the same. So so let's say you run across multiple nodes, right? In the same node, because the local rank ID is start from 0 until that n-1 rank.
Yeah.
And so it's all the same. And so they all map to the same core ID, the same PVC tile, the same memory module. Any question?
What happens when we do multiple for example,
so let's say I'm running across 2 nodes, then I have 24 ranks, right? So my MP exec would be 20. Let's say I run 12 ranks per node. Then MP exec would be MP equal to 24 minus PPN 12. So 12 process per node, 24 rank total. And on each node, each of these 2 nodes, the local rank ID will be 0 to 11. And then use the local rank ID to calculate all this, right? And then map to the right memory and PVC tile. You're on 24, then 24 rank per node, then the total number of rank will be 48, and the rank per node would be 24. And so for most of the application, the acceptance application, we use something like this. I'll go into machine learning in a bit later, right? It's slightly different, but for most application, you want to specify the CPU list, CPU ID, the affinity mask for PVC, and then the memory module that you want to use. And here we prefer, and we use, let's say, HBM. And if it run out of space on HBM, then spill over to DDR. But you can say that, I want really it come from memory, and if you run out of memory in HBM, then the application will not run, it will crash. Then there's an option to do that, to force it. So now this part is more of the traditional, of the original intent of the talk was, how do we scale application? And I say go back here, right? So for the CPU binding, most so for something like Retina 50, we use 12 rank per node. For Cosmic Tiger, we run 2 ranks per tile, 24 rank per node, mainly because Cosmic Tiger doesn't scale, doesn't use all the available compute on a GPU. So there's it cannot fully utilize. So in this case, you can run another process on the same tile, and so they would share that tile. And for PVC, you can explicitly partition the tile into 2 physical equal number of EUs for each process, and then they would run exclusively on their portion of EUs. And here for 96 rank per node, in this case here, you have a lot more thread that map to a PVC tile. In this case, when they use these rank, then for PVC, each tile has 4 contacts, and you can run up to 4 rank per tile without context switching. But when you run more than 4, then you do context switching. But I think for Kimsey Pack, it uses thread, and it rely on the Open MP runtime to map those threads to the tile. So for Aurora, we scale several applications, right? Pretty much all the we have 11 applications, and we try to scale to the entire system. And so LAM is one of them. Now, LAM is a little tricky in that the main computation loop takes about just a bit over 3 seconds, and then it does a reduction, and then it does that again. So the compute portion is very small between communication. And so when you run with 512 nodes, it's not so bad, right? But when you run at scale at 10,000 nodes, if there's any hiccup in traffic in the network, let's say there's timeout or there's some delay, then the main loop, because the time is so short that it is sensitive to any variation in the network traffic, and so it doesn't scale well at 10,000 nodes when the main loop time is very small. So 2 optimization was done. One is to change the mapping of assignment. The initial assignment used a single mapping where it assigns atoms or elements to node, and those are assigned to 96 ranks. Eventually, there is some imbalance. In addition, we have the small loop times, and so to address the first issue, which is the mapping, they use 2-level mapping. There's one local grid and one global grid. So the local grid is per node, and what they did is they sort this local grid to improve cache locality. And that also helped with the check. So by using 2 grids, the number of checks are less, and the overhead is less. And they didn't see much improvement when running with very few nodes, but at higher node count, that provided a very good improvement. For loop time, small loop time, I think something like 3 seconds or 3 or 4 seconds, right, in the loop time before all reduce. That's too small. So in this case, they have to increase the amount of compute between communication, and that help increase in the compute portion, and that make it less sensitive to any noise in the network. The other thing is that the HPM module on Sapphire Rapids actually help with performance over DDR. That's a little surprising. I thought that a LAM would be more cache bound, but there are memory bound portion in the code, and HBM seems to help here. Any issue here? Any question? We move on to hack. So hack actually was ported from CUDA. Initially, there was many small kernels, and we found that fusing the small kernel into a larger one, and then fusing the communication over PCIe between the host and the device into a larger data transfer help amortize the overhead of the transfer, as well as allow you to have enough compute so that you can overlap compute with communication. So that's one optimization. The other one is to use the high memory bandwidth on Sapphire Rapids. So there are still portion of code you can see here running on a CPU that is memory bound, right? So particularly the tribute, where you see that by running on HBM, it's 1.4 times faster than running on DDR. And the other portion also. So here, by mapping, you can map specific array, or you can map the entire application to Sapphire HBM and get higher bandwidth and shorter memory time for these modules, these kernels. For QMC pack, this is where you use a lot of OpenMP thread for parallelism, and the number of PC thread per core, it depends on the problem size, but for the Aurora system, we found that assigning one OpenMP thread per core works well. And because there are many small offload kernel, that's why we want to run with multiple OpenMP thread, and each OpenMP thread has an in-order queue. So the runtime would try to overlap these queue to maximize parallelism. The most important thing is to prevent any cross-thread dependency, so that the runtime can execute these overlap this queue and execute multiple threads at the same time. Now, for machine learning, for optimization, most of the optimization went into the machine learning framework and libraries. So 1DNN is, you can think of 1DNN as like MPL, where there's a lot of these machine learning kernel are optimized in the 1DNN library, such as convolution and GEM for skinning matrices. And so all the math is done, it's provided by 1DNN library, and communication, like all reduced on, is formed by 1CTL library. See. So for optimization for this application, right, so right. let's see. So for machine learning, particularly for distributed training, there's the fast link. There are two fast scale-up link. One is between the two towers on the same PVC. And there's another fast link, which is the XE link that connect all the GPU together. So like a typical all reduce would perform reduction tile to tile first. Right? And then after tile to tile is done, it use the fully connected XE link XE link communication fabric to do reduction from among PVC. And then if you have scale out, then that is transferred to the host. The data is transferred to the host for host to host reduction. And then so that go up, right, and reduce, and then that propagate down to the tile again.
And then a couple of remnants.
Okay.
Your slides.
So for S950, to optimize this, we use Chrome Trace. We plot out in timeline all the operation. And initially, it was used to find, how much time was spent on each kernel, right? Convolution and so on, and whether they perform to, roofline models. And if they underperform, then we inform the 1DN team to optimize those kernel. For communication, initially we found there was overhead in communication. There was overhead in copying the tensor from different locations to a buffer for communication. And so that has to be optimized so that you can overlap computation with copying. And then when communication is performed, right, the data is always in buffer. As I mentioned, like process binding, we use trail rank for trail tiles. And actually there are more mapping than just the main application processes. The communication library spawned its own thread. So that is now, we use another core for each rank for communication for CCL. PyTorch spawned its own worker thread, and that used another core. And Horrobot also has thread, but interestingly, it likes to share that core with the main process. The other thing is that for something like ResNet50 distributed training, we don't set the ZF50 mask, because when you set the mask, then CCL see only one PVC tile for each process. And PVC like to discover topology, so it wants to see all the trail available tile, and then it will try to map the offloading process onto the right PVC tile. So here we leave it untouched, right, unset, and let CCL do the topology and set the mask for the rank. There are other applications that run in a throughput manner. And so, for example, you take the machine learning application from Argonne, kind of Uno. Each process use only a quarter of the EU because it has very small gems. And what you can do is, in the case when you explore parameter search, right? We want to see whether you find a set of parameters that provide better conversion. So you can run this in a throughput mode where each rank is used for a particular parameter search, and 4 ranks would run on the same tile. And the only issue with this is that all of them try to read the data set at the same time. And so imagine that you have 48 ranks per node, all of them try to load the data set, and you run it on 10,000 nodes, then you have a lot of rank, and file system cannot handle this kind of thing. So what we use is a Python utility that read. So it read and distribute. It perform only one single read, and then it uses Slingshot Fabric to broadcast the data. or to propagate the data. In that way, it can scale. The other thing is that any checkpointing, any logging, anything like that to the file system should perform on the local node. So what we use is /temp, which is RAM disk, right? Which is SSD. And so all that is written onto a local node and only copy back when you need a particular, after the run, or when you need a particular piece of data. And if you don't need most of it, then it's good to discard. And something with Thunder SVM, which is a data analytic, where instead of using that Python utility to broadcast, it uses MPI broadcast mechanism to distribute the data set. So summary is that for Aurora, there are one single node. You can treat it as two separate nodes, two separate domains, and you try to isolate or contain them within that domain. So the process would map to the core and the PVC and the NIC on the same domain, so that you don't cross the domain and pay for in higher latency or low bandwidth. And CPU binding and PVC affinity and memory bindings are important. Default should be okay to start out with, but it's good to map them to target the specific needs of your application. That's it.
Good, thank you.
Right.
We have time for a question or two.
Yes, so any question?
I have a question.
Go
Can I
ahead.
ask? Yeah, so the question is, did you happen to leverage the precision AMX library, which helps you to use the reduced precision rather than using the double precision or the single precision?
No, I
So
didn't.
I'm asking the machine learning applications that you gave the example. So did you use, what precision did you use, and did you also try the lower precision to improve the performance?
Low precision to improve performance.
Yeah, the 16-bit or sensor TF32.
So some of them, I think for the HPC benchmark, they are FP64, right? So for something like Hack and LAMP. For Resnet 50, we use FP32. We also try BFlow 16 and TF32, which we do precision for improved performance. Yes, so performance does improve, but not as there are communications. So I'm not sure whether we reduce the size of the data transfer, so the communication may still be the same. The compute portion did improve. Good.
Yeah, so I saw some benefits over the OpenFold when I run with TF32, and there is an operation called matrix multiplication mode, which if you specify BF32 or TF32, it gives you pretty good performance compared to the just FP32. Yeah.
Yeah. So for Aurora, the ResNet that we use, we try to strong scale the problem to as many nodes as possible. In fact, each rank has processed only a mini batch of 16 images, which is quite small. So traditionally, you want to use 512 or 1024. In this case, we want to strong scale it so that we actually run a single instance of ResNet 50 distributed training across 171 nodes, and that is 2,048 PVC tile, and which each tile having only 16 images per batch. So the amount of compute actually is quite small. So we use reduced precision, then the amount of compute will become even smaller, and communication will dominate. Okay. But let's say if you run on fewer nodes, right? So we try to run up to 32, a global batch of 32. Larger than that, you would run into convergence issue. And if you run on a fewer number of nodes, then the batch size can be larger, right? And the compute portion will be larger, and you can use reduce precision to reduce compute time.
Good. All right. You had a question? There.
I was wondering about the CPU actually. Yesterday in the technical program, there was a presentation about GPU usage on Aurora as well. Did I got it right that the CPUs are configured that you have like 4 NUMA domains, or is it?
So there are several ways to do that.
Yeah. That's what I'm wondering.
So one is called SMC4, flat. So the flat SMC4 flat is that you treat each memory module separately and you use them separately. And so with SMC4, you divide the CPU memory into 4 quadrants.
Mm-hmm.
And so there are, HBM will get divided into 4, DDR will divide into 4. So you have 8 different domain
And then
CPU.
the question was like, you have like the first NUMA domain, which is basically attached to 1 GPU. You have the second NUMA domain, which is more or less attached to like 2 GPUs. And then you have like the third and fourth NUMA domain, which are not attached to any GPU.
Right.
And the question yesterday in the session was like, what was the rationale behind this design choice? And it was not clear to the audience.
Yeah, so that research doesn't make sense, but it has to do with the layout of the chip and the number of ports available that you can tie to. So you have I/O port, you have other port that you have to tie to. So they decide to tie 2 PVCs to one, another PC to another, and then the other was used for I/O, and which is limited number of pins that you can have, and that's how it come out to be that way. So it's just physical constraint, not logical.
Okay. Yep.
So first, I want to clarify the optimization is done here for the SQL version of the code word, the GPU version, not the CPU.
For the
The optimization you show here is for the GPU version or the CPU version.
It's well, you have to. The idea is to map a process, right, to a core on the host side, and then to a particular GPU tile that have a more connection, right, to that particular core. So let's say you map to this core here, the second core, the core on the second CPU, and you can see here you have these PCIe linked, right, to these 3 lower PVC, and so you want your offloading portion to land on any of those PVC tiles, but not on the other one, right? On the other one, then you have to communicate through UPI, which is a narrow bandwidth. You have to transfer over there and then communicate with PVC. So it's good just to draw a line across, right? And then keep all your processes in this on the same area.
So in case of Aurora, the scheduler is configured to have exclusive access. So the user cannot share the resource of one.
Right. Right. Yeah. So when you allocate a node, then pretty much you have exclusive use object, right? So this is when you have multiple processes running, and you want to make sure that when the process offloads to a particular GPU, right, and it has the full bandwidth of PCIe and not having to go through another socket or another CPU in order to communicate. Same with the NIC, right? So initially we have to, be aware of the NIC, where the process use which NIC. Now MPI and NIC handle all that. So if you process it on, one particular side, then we use the NIC from that side.
Probably stop there. Thanks again for all the thorough stuff.